Okay, you guys, we're at like possibly the most central lesson. I put two sections of our book together here. Triangle congruence shortcuts. Okay, so in the last video we talked about the definition of two triangles being congruent. That's all their quantifiable measurements are the same. We narrowed that down to the three sides and the three angles are the same. So if we know all three sides and three angles are the same, two triangles are congruent. And vice versa. Two triangles are congruent, then we know all three sides and all three angles are congruent. The big picture here is, instead of finding all six, three sides and three angles, it's actually sufficient to find just three pieces of information are congruent. Now the whole point of this video is to see which three we need to find, which three are sufficient, and then use it, both in proofs and algebra, mostly in proofs, okay? Now here's the shortcut little table. I'll go over it again afterwards, but these shortcuts on the left are the ones that are sufficient, and the ones on the right are the ones that are not sufficient, okay? All right, I won't even introduce them now. I'll introduce them one by one. All right, so important vocab before we move on. I'll zoom out a little bit here. So an included angle, what I mean is, if I'm talking about two sides, right? If I'm saying, oh, you know, this side here and this side here, then the included angle is the angle that those two sides form, right? The angle in between those two sides. So when I'm talking about the two congruent sides, then the angle between them, that's the included angle. And same thing, the included side is, if I'm referring to two angles, like angle A and angle B, the included side is the side connecting those two angles, right? So literally the one sandwiched between the two angles, that's what we mean when we say the included angle. Okay, we're gonna use that as we state these theorems and postulates. Okay, let's go. So first congruent shortcut, side, side, side. So if all three sides of one triangle match all three sides of another triangle, then biconditional, if and only if, that means the two triangles are congruent. Okay, so if triangles are congruent, then all three sides match, of course. But if three sides match, we know nothing about the angles, it is sufficient to know that now we know the triangles are congruent, okay? So order matters, so I'm just going to fill in this example down below. Okay, so A to B to C. So A to B to C, the journey would go like this. So it would go across this side with the 1 hash mark and the side with the 2. So I know that since all three sides are the same, it's the same as this triangle. I just need to get the order right. So going across side 1, then side 2, that would be this journey here. And so that's triangle X, or no, Z to Y to X. So Z to Y to X, that order absolutely matters. And the reason there would be, I'm sorry, move this over, SSS Triangle Congruence, okay? The reason I say that is we are going to have an SSS later on about triangle similarity, okay? So that's why I say triangle congruence. All right, so think about the Y. If I take two sides, right? And so these two sides are kind of like on the hinge, okay? I could, now I'm not doing a good job of keeping it hinged, but like I could swing this around this way, but the length is determined. But where do I swing it? Where do I swing it? Well, the only place I can swing it is so that the distance remaining between these 2 points is the length of the third side. So if I take that first side and I go, okay, I'm just swinging it, right? I would only be able to swing it until this side length, and now my version here of moving this around doesn't keep it the same distance. But the only way I could form a triangle is by swinging those two sides until the opening between them, the distance between these 2 points, exactly matches the third distance, right? So we absolutely are talking about the same triangle, right? If I give you 3 straws of 3 lengths and I say, build a triangle, the only one you can make if those lengths are determined is the triangle that I made, right? You take any 2 and then your partner says, okay, you take those same 2 and now just move them apart and together like a hinge until they are the length apart of the third straw. Done. Your triangle's the same as his. That is enough to narrow down all of the triangles in the universe to say me and you are talking about the exact same triangle. These triangles must be the same, okay? All right, another shortcut is side angle side. So now if we have any two sides of a triangle and the included angle, so if I'm talking about these two sides of a triangle, the included angle is where those two sides meet. Those two sides form an angle. So if the two sides and the included angle of one triangle are the same as this side angle side sandwich of another triangle, well, then the two triangles have to be the same, right? This y is even easier. Like, think about it. I've got two sides and the angle's determined, so I can't even hinge them at all. Like, the angle between them is set. The two side lengths are set. There is literally no other possibility. That is done. All you need to do now is connect these 2 points, and that's the only triangle that exists with those two side lengths and that angle between them. Okay, so let's go up here. Now, again, I'm going to kind of travel this journey. I'm going to say, let's go across side 1, then side 2. Oh, no, sorry. It was already determined, ABC. So ABC. So from A to B to C, I went across the side with 1 mark, and then the side with no marks. So the only way to go across the 1 mark and the no mark side was to go Z to Y to X. That was the journey there, so Z to Y to X. And again, this was by the new side angle side triangle congruence. And we're going to practice a lot of these towards the end, okay? Now, here's one that does not work, okay? So don't be an ass by assuming that ASS means triangles are congruent, okay? So that's funny, right? Like, oh, assuming makes an ass out of you and me is the classic pun. Okay. So the angle must be between the two sides, SAS. That's what we just did. If the angle is not included, so if I have two sides of a triangle and I don't know the angle between, but instead I know this angle over here is the same as in another triangle, there's two sides and the angle is not in between, that's not enough to narrow it down. And the Y we can see over here, okay? So I'm going to just erase this really quick. Okay, so looking at this, I got an angle and two sides, but notice the angle is not between, the angle is not sandwiched between, so it's not SAS, it's outside. So what that means is we got this side locked in. This hinge can kind of just hinge anywhere, right? I go, okay, well, I can open and close these two sides as much as I want, but this angle is set. So we have to have that third side land here. Is there anywhere else it could land? Well, what if we swung it? Bam! So if we take this side and we swing it and we go, whoops, it's all one line. Sorry, I got to redo this really quick. I thought that was two separate lines. And then we make it two separate lines so I can swing it. Okay, so let's take this now, and if we swing it down this way, oh my gosh, swinging it is difficult. Okay, let's try that again. Okay, and if we swing it down, what ends up happening is there's another spot that it hits. Okay, and so what that does is that gives us two possible versions. So we have this triangle with this angle, this side, and we have this triangle with this side, and this angle. So they have the same angle side, and yet they're two different triangles. So this is not a sufficient amount of information to determine which of these triangles we were talking about. Now, it does, I wrote off to here, it does narrow down all of the infinitely many triangles down to two possibilities. Now that's pretty good. Narrowing down infinity to two, that's pretty good. But still, it's not unambiguous. We do not know we are talking about the same triangle, so we cannot reliably use this one. Okay, so again, it's the same ASS information in these two triangles, but they're different triangles. So we cannot use ASS, okay? It's not sufficient to know. And then I made sure to be clear, ASS and SSA are the same thing. If I know two sides of a triangle, any two, like say these two, it doesn't matter whether the third angle is here that I know, that's not included, or whether it's, whoa, or whether it's, whoa, that's crazy. I zoomed in, I've never seen that before. Or if it's over here. Okay, if they're not between the two sides, then it doesn't work. That's ASS or SSA. The only way we know this is if it's S and then AS. So if it's the angle is included between the two sides, that is sufficient. Okay, But then a little loophole. But ASS does work, does it? What? I just said no. So don't get confused here. ASS does not work. However, when it's in a right triangle, if we know two sides in a right triangle, we can use the Pythagorean theorem, which only works in a right triangle, to get the value of the third side. So actually, in a right triangle, it does work. So we give it a separate name rather than saying ASS, but in a right triangle. That would be unclear since ASS doesn't work. So instead, we call it HL, or Hypotenuse-Leg. And see how we've got ASS. We've got three pieces of information. The three pieces are two sides. And look, it's not the included angle, but the reason it works is because that not included angle is a special case. It's a right angle. And so we could use the Pythagorean theorem with whatever two values these are and express this third side as a value of those. And so we go, oh, it must be the same calculations on the other triangle as this, right? It's the same reasoning we used for, like, if I know two angles are the same of two triangles, then we could say, well, since they sum to 180, we have an algebraic relationship that we can use, and that algebra then tells us the third angles must be the same. Well, we have an algebraic relationship in the right triangles, which is the Pythagorean theorem. So we can say algebraically that third side must be the same. So we could even call that the third side theorem in a right triangle, but we don't need to. We'll just call it hypotenuse-leg. And let's go ahead and finish this one. So in this picture, I scribbled all over it, which I know is super helpful for reading a diagram. And so let's look at this. So we have ABC, so that's this way. So we went across the one side and then nothing, or my extra mark. And so then we go across the one side and the nothing. So that would for sure be DFE. And the reason there would be HL triangle congruence. Okay, so let's now go to the second to last one here. So ASA, angle side angle. That means if we're given two angles and the included side between them of one triangle are the same as two angles and the side between them of another triangle, the two triangles must be congruent. Again, the Y for me is really helpful. Oh, I didn't draw a picture here, but the Y is really helpful, right? If I start with a side length and then I say from this side, shoot in this direction, like the angle set. And I say, oh, and from this endpoint, shoot in this direction, that angle set. Well, there's only one place those two lines could meet. They could only meet at this point. That's the only triangle we can form, right? This side length is set. This angle is set. This angle is set. There's no flexibility here to make another triangle. Like, that's the only triangle that can possibly be formed. Okay, so let's do this. So ABC is this way, ABC. So that's one angle, none to two. So one angle, none to two. That's ZYX. Okay, so ZYX. And then the reason here would be there were two angles and there was a side between them. So that was ASA, triangle congruence. All right, and then last one here that works is the angle side, or the same thing as side angle. So what matters is we have two angles and then we have a side that's not between them, right? It doesn't matter which side that the marking's on so much, but order does matter actually. So we have two angles here and here, and then we have a side not between them. Now order does matter in the sense that if the marking is right here adjacent to the angle with two arcs, if on the other one it was on this side, that would be a mismatch. You would say no, that side has to be adjacent to the angle with two dashes. So order does matter in that sense, that you can't have a triangle that is actually different, right? Like the side is in an impossibly different spot where no rotation or flip would create that. You literally took two sides off the triangle, flipped them around, and glued them back on in a different order. Now that's a really cool thing to talk about. That's actually, I think in chemistry it's called the chirality of a molecule, where it's the same building blocks, even in really simple molecules with just, 4 or 5 atoms, but you have the same atoms snapped together in the same way, but one's like the mirror image of the other, and that can actually lead to different treatments where the chirality in one molecule does fit and the other doesn't, left-handedness, right-handedness. It's a cool thing to talk about, but in this, it's just something to check. It rarely comes up in geometry. Okay, So we got those two angles, and on the correct double angle side, we have that side there. And so yeah, then we do know these are congruent by AAS. And this is, let's just go ABC. So that's angle with one arc to none to 2. So one arc to none to 2. That's again ZYX. Okay, and then the reason there was AAS or SAA, same thing. Triangle congruence, okay? And the Y, think about it, okay? So I've got this like this angle here, okay? And then I've got this side length too. And then I can do any side length here, but I do have this angle lined up, right? I do have this like this angle is set. And so all my flexibility here really is I can slide this point left or right along the base, because this angle on the bottom was set. I know the direction of this bottom line, so all I can do is slide this point left or right. Well, there's only, if the angle here is set, there's only one location on this bottom line where this would line up and shoot right through this point. So I'd have to slide it a little bit right to about here so that that angle would line up. There's only one place that point could be. And if there's only one place that point could be, that means that anybody that forms this triangle, starting with this angle and this angle, and knowing this side next to the one arc angle, then the only place they could put that third point is right here, and we would all create the same triangle. There's no ambiguity. So again, I'm not proving these rigorously. Most of these are postulates. We're just agreeing that it's logical, that yeah, that must be true. Okay, and last one, here's one that doesn't work. So AAA doesn't work. If you know all three angles of one triangle are the same as another, that does actually tell you they're the same shape, but it doesn't tell you they're the same size. And so I could, whoa, I'm doing this, but I could zoom in or out. Now, this picture of Batman is staying the same. It's just changing its size. It's just fun to do. That's what happens with AA. So you always need at least one side length to tell you the size of the object. So that's why AAA doesn't work. AAS works because you have that one side. Okay, so let's just summarize them all really quick. So in summary, pretty much every combination works out of 3 facts. So all but 2 combinations of 3 sides and angles work. So for example, if we have 3, so out of the 3 facts, if they're all 3 sides, check, it works. SSS, we're good to go. What if instead of 3 sides, we had 2 sides and 1 angle? Well, if the angle's between the 2 sides, we're good to go. SAS works. If the angle is not between the 2 sides, that's the ASS. Or SSA, those are the same thing. So that one doesn't work, okay? And so it's easy to remember with the don't be an ASS. Like that's an easy one to remember. And then what if we have 1 side and 2 angles? Well, really what's happening here, I wrote it off to the side. If we know 2 angles, then the third angle theorem says, actually the third angle must be the same too, which then means the 2 shapes are the same. All we need to do is know 1 single side matches so that they're the same size, and then, oh yeah, it doesn't matter what side we have, as long as it's corresponding, then the 2 shapes are not only the same shape, but they're also the same size, so all of these work. Whether it's 2 angles and the side between, or 2 angles and the side not between, it works. Because 2 angles means the whole shape's the same. That's actually something we're going to talk about a lot in future chapters. And then we need 1 side. Whether it's included, so ASA, or not included, AAS, doesn't matter. And again, SAA is the same thing. Okay, and lastly, what if it was just 3 angles? Well, that's not enough. We need at least 1 side length to tell us anything. I mean, is this thing the size of an ant, size of a marble, the size of a desk, the size of a planet, the size of a galaxy? I mean, the universe is immensely, unimaginably large. How big is this freaking triangle? Okay, all right. So now let's do a couple non-proof practice. There's still 1 or 2 big important lessons left, so don't cut out of the video yet. Okay. So I would recommend going to IXL and practicing K1, K3, and K5. So that's before proofs. That's just saying, can you identify congruent triangles and correctly use the postulates above, okay? So let's use it. Now, they aren't given all of the information. We need to take extra steps. So I see 2 triangles here. Okay, what's congruent between these 2 triangles? Well, they have 1 side is congruent. Oh, and they have one angle is congruent. If only we had a third piece of information. Well, look at this. This triangle on the bottom shares a side with this triangle on top. And we know that side is the same. It doesn't matter whether we're talking about that side in the bottom triangle or in the top triangle. By the reflexive property, it's always congruent to itself. So in this triangle, we have SAS is the same as SAS in this triangle. So yes, and that's SAS triangle congruence, okay? Now let's look at this one over here. Oh, same thing over here. These two triangles, we have two pieces of information. We need a third, and that third is that they share a side. And that shared side is always congruent to itself, right? If you took these two apart and just had this, you say, oh, well, that's not enough information by itself. But the picture with them lined up is telling you that these sides match. And so 1, 2, 3 dashes, again, that'd be the reflexive property because any side is congruent to itself. And so this would be yes. This is the SSS triangle congruence. Okay, down here, we got the same thing. We got what side is equal to itself. But that's not enough. We just have one side and one angle. But then we look a little deeper and we said, what else is in this picture that we could maybe use? Well, I see parallel lines. Anytime I see parallel lines, my head is thinking, probably we're going to use corresponding angles or maybe alternate interior angles. There's other relationships, but those are the two most common. Well, I'm not going to use corresponding here, but we do have this like zigzag transversal. So between this line and the transversal, we have this angle formed, transversal and side, and then transversal and side form this angle. So we do have these two angles match, alternate interior angles. Well now, oh, and I'll put two arcs there. I'll use pink. So here's a 1, 2 arc, and here's a 1, 2 arc. So now in this top triangle, I have two angles and a side not between them. So that's yes by AAS. Or you could have said SAA, right? So it's two sides. I'm stumbling over my words. We knew two angles were congruent in the two triangles, and then the side is not between them. Whether the side is first drafter doesn't matter. Okay, so, and then triangle congruence. Okay, and this other one up here, we've got, again, parallel lines. So again, between parallel and transversal, we get alternate interior angles are congruent. And we could do that same thing again with these two angles, but instead I'm going to shake it up and do something different. I'm going to say we also know vertical angles here. Okay, and if we know vertical angles, this is also yes by AAS or SAA. Now notice, what if I'd done this differently? So I'm going to pretend I'd done this differently. So I'm going to cross that out. That's correct. Okay, but I'm going to instead erase this and say, well, what if, whoa, that was a big erase. What if instead the angles that I'd use for alternate interior is maybe I went with this one is congruent to this one. And now I used these three and these. Oh, look at that. You know what? I was jumping the gun. I put this one in here to trick myself, and I went ahead and tricked myself. I fell for the booby trap. Do you notice something? Right as I was trying to circle that, look at what happened. I said, okay, well, these three ASA are the same as these three AS. What happened? No. And look at that. So the vertical angles line up, but look at the angle marking. So alternate interior angles, this one matches this one, but the side here is between angle marked 1 and 2, and over here it's between angle marked 2 and 3. So actually the answer here is no. These are not necessarily congruent. Maybe they are. Maybe this is like an isosceles triangle where all the sides are the same, equilateral. You know, there are possibilities, but we do not have enough information. So we're going to say not enough information. Oh, I tricked myself, but then caught myself, because at the end, whenever I say the triangles are congruent, I go in order to write it out. And that's when I said, wait a second, the order doesn't match. Okay, good call. What about this last one? Well, we've got this isosceles triangle, and we've got right angles. Is there anything else we know? Well, again, this triangle and this triangle share a side, and so this side is congruent to itself by reflexive. And so look at what we have. We have a right triangle with the leg and the hypotenuse. So without a right triangle, if this was just any old angle, this would be ASS, so this would not be. So we'd have two sides and the angle not between them, so ASS would not work. But because it's a right angle, then we do know that hypotenuse-leg, so yes, by hypotenuse-leg triangle congruence. Okay, let's do one more over here. So again, we share a side, so this is congruent to itself. Here we have ASA matches ASA, so yes, by ASA triangle congruence. Okay, so now let's do two proofs, and then we'll get to our last piece of this lesson, which is Cpctc. Okay, you're like, well, I already know that. Well, just wait how we're going to use it here. Okay, so let's do a flow proof here. So we start with, let's do blue. Okay, so we start with X is the midpoint of BD. Okay, that's given. Okay, and then you can already probably guess how we're going to use that, right? Well, how do we ever get from a word to math, right? Well, the way we do that is by using the very definition. So I'm going to do the same thing to both of these. I'm going to say, well, that means that if X is the middle of that, then from X to A is the same as from A to C. Now, I'm okay with you using the definition of midpoint to say either the values are equal lengths or the segments are congruent. Since we're trying to prove triangles are congruent, I want congruent segments. I want geometric objects are the same, because that's what it takes to show triangles are congruent. I don't want equal lengths to go to algebra. There definitely are proofs where I want that. We've done a lot of those, but not in this case, right? And so I'm going to erase this and do this just to me in a better order. So from A to the middle point X, and then I was speaking and writing, so I messed up, then it is the same as from X to C, okay? And then X to C this way. Okay, so from B to X, okay, that's congruent as from X to D. And both of those just use the definition of the word, right? So we use the definition of that given midpoint here and the definition of the midpoint over here. Okay, so now we've got these two. I'm just going to mark them on the diagram. That's helpful for me. So B to X is the same thing as X to D. And then we also know that A to X, different, is the same as X to C here. And so what else do we know? We want to show that DXE. So we want to show that this triangle is congruent to this triangle. Well, what's the third piece of information we have here? Well, we don't have anything about the third side, right? So we can't use SSS. I mean, I don't see any way we could logically get that right now. And let's see, we don't have these are parallel, because if these were parallel, we could say alternate interior angles are congruent, but that would only give us ASS, and that wouldn't even help us. Okay, well, that's not it. Oh, wait, look at this other angle relationship. We have vertical angles here. So what I'm going to do is I'm going to take this and slide it over. And I'm going to take this and slide over, and right in the middle, I'm going to go ahead and say, well, angle DXC is actually congruent to angle AXB, and that's by the vertical angle theorem. Now, if you wanted to be really clear, you could absolutely say angle DXC and angle AXB are vertical angles. And the reason they're to say they are vertical angles would either be given by diagram or definition of vertical angles. That's how you identify them in the picture. But it's not here the definition that says they're congruent. We proved that using algebra and linear pairs. Okay, so now that we have those three pieces are matching, we have these three pieces, two sides in the included angle, two sides in the included angle. So now the two triangles must be congruent. So I bring all three of these together. It takes three pieces of information to say triangles are congruent, and I need to match the order correctly. I mean, the order is given here, but I'm going to double check it. So we say it's triangle D to X to C. So in my picture, just zooming in, D to X to C goes like this. D to X to C goes across 1 dash, then 2 dash. So that has to match 1 dash, 2 dash, BXA. And sure enough, they got the order right. So BXA. And how did we know that? Well, that was two sides and the included angle. So there's two sides and an angle between them. So that was SAS triangle congruence. Okay, so that's a good, just clean proof there for you guys. Okay, let's do one more, and then we'll do Cpctc, the last piece of this lesson. Okay, so we're given that these two sides are parallel. That's written in the picture. We're given that TXY, you could have just called this angle X in the given and angle S. So those two are congruent. It marks it. Okay, good. So let's start with those. So we've got this TX is parallel to SY. Okay, and we want to show that two triangles are congruent. So how are we going to use that? And then we also have this, I'm going to abbreviate it to angle X is congruent to angle S. So both of these were given, okay? And I can slide these around. That's why I'm just kind of throwing them both down now. Well, I do know I can say that this side, because I want to show that two triangles are congruent, I can say this side is congruent to itself. I can always say that. So I can say TY is congruent to itself. That's going to be one of the three pieces of information, and that's the reflexive property of congruence. Okay, so we got three pieces of information, but this isn't a side or an angle that's congruent. So how can I use that? Okay, well, if those two lines are parallel, that means these two lines are going in the same direction, and then they're connected by a transversal here. Well, that means the angle between transversal and line is the same as this one. Now, common mistake is people identifying this one and this one as congruent. They are alternate interior, but they are alternate interior in terms of the left and right sides. So we don't know that those two sides are parallel, so we know nothing about the starred angles in terms of are they congruent or not. But we do know that angle XTY must be congruent to angle SYT. That is what these parallel lines tell us. They tell us nothing about these two starred angles. We know nothing about those because we don't know that those sides TS and XY are parallel. And this one's by alternate interior angle theorem. It's the forward, or you could say alternate interior angle biconditional. I'm okay with that too. All right, so now we want to show that the triangles are the same. So we have this angle matches this angle. I'm going to erase those stars now. Okay. So let's look at this. Do we have enough information? Well, we have two angles. Oh, I need two dashes for this, two arcs. Okay, so we have two angles and a side knot between them. So two angles and a side knot between, that's two A's and an S knot in between. So yeah, that is enough. We can say the triangles are congruent by two angles and a side knot between. Triangle congruence, that's AAS. Great, so I'm going to just slide these down so they all line up here nice and pretty. And then we could slide this down. And slide this down, and look at that. I even lined it up to be angle, side, just for aesthetics. That's nice. Okay, now we just need to get the order right. So it started with TSY, so triangle, TSY, and I always check my order. It's a way of catching myself from any mistakes. So TSY is across no angle, one angle, two angle, and I'd never come across that side. So no angle to one angle to two angle would be YXT, and sure enough, that's the order they have. So triangle YXT, because sometimes they'll do the wrong order, and then you say this proof can't be done. We don't have enough information. All right, so the last piece of this lesson is Cpctc. So how we really use Cpctc is this always comes right after we have congruent triangles. And again, this is basically just saying the definition of two triangles congruent. If the triangles are congruent, then we know all of their parts are congruent, right? Or all the corresponding parts. Now, this is very often the last step in a proof. So if we do a proof, and before this right now, you've just gotten, okay, the two triangles are congruent and this last part doesn't exist, right? You go, okay, I did all this work. The two triangles must be congruent. Like this is a real proof that I wrote for you. But then we can use that and say, well, I only had the pieces that I knew. I knew three facts. I knew side AX is congruent to MX. I knew side BX is the same as side XN, and I knew the vertical angles. But I know nothing about angle A is related to angle M. I know nothing about angle B is related to angle N. I know nothing about AB and MN. But I actually do now. Now that the triangles are congruent, I could say all of those things. I could say, well, I also know that angle A is congruent to angle M, right? And that's by the corresponding parts of congruent triangles are congruent. And I also know angle B is congruent to angle N. And again, that's by CPC. It's just saying the matching parts are the same. Cpctc or you could say definition of congruent triangles, but every single book uses Cpctc, so I think that's a useful acronym. But this is very often the last step in a proof. And really, this is one of the most common ways we prove anything in geometry. So if I say, here's a proof, prove these segments are the same, 90% of the time, what you're going to do is find two congruent triangles and say, now I know those two pieces match because I found the two triangles are congruent. Or if I say, hey, go ahead and find these two angles, I want you to prove those two angles are the same. Again, like 90% of the time, especially in this chapter and moving forward, you're going to do it by finding congruent triangles. And then after you found the congruent triangles, you'll go, okay, since I did that, then I know all their parts match. Boom, I got the segments congruent. Just the ones you wanted, Mr. Dilloughery. And I would clap and bravo, well done. And the whole class slow clap and like emotion and montage. Oh, it's going to be great. Okay, so here we go. Let's do a couple proofs. So here they mention nothing about congruent triangles. They just say, I'm given a couple facts about segments and angles, and I want you to prove this angle. And in the past, all we really had was segment addition postulate and angle addition postulate. But now, you can go ahead and say, well, now I can find congruent triangles. And if I find congruent triangles, right? So all I need are 3 pieces of information to get congruent triangles. Not any 3, right? We picked which 3. And then once I get that, then I know 6 facts. Right? So that tells us 3 new things. So if I find 3 sides are the same, then I know all 3 sides and all 3 angles are the same. Right? That's the ability here is we use a shortcut, a triangle congruence shortcut, to get the triangles are congruent. Then we know all 6 things. Everything, actually. We know even the altitudes match, the angle bisectors, anything that's corresponding matches. Okay, so let's actually go ahead and do the proof now. Enough yapping. Okay, so let's look at this. Well, given in this picture, we have everything marked there. Well, what else do we know? Okay, we don't know parallel because this is alternate interior with this, and then we aren't given those things. We can't get parallel sides. Oh, well, look at this. We can get vertical angles here. Okay, so let's write this. So we have WX is congruent to XY. That was given. Oops, I forgot the little bars over it. We were also given angle V is congruent to angle Z. Okay, well, I almost put a bar over that, so that was given. Okay, and then what we established separately is angle, you cannot say angle X is congruent to angle X. That's ambiguous, right? If you're going to name this angle, because there's tons of angles at angle X, you need to use 3 letters here. Okay, so let's name it. So we're going to say angle VXW is congruent to, by the way, you could say like angle V is congruent to itself because there's no ambiguity. That's the reflexive property. So you can always say an angle is equal to itself. You just can't name something angle X in this picture because there's tons of angles there. That's what I meant. But you can for sure say an angle is congruent to itself. Okay, and so angle VXW is the same as angle ZXY, and that's by the vertical angle theorem. Okay, and with those 3 powers combined, we have 2 angles and a non-included side, or 2 angles and non-included side. Notice the 2 dash is next to the 2 dash, so it's in the right order. So we've got, yes, with these combined, the triangles are congruent, and that's by AAS, triangle congruence. Okay, well, let's write the order. So I will start in the top one. I'll go from the 1 arc to 2 arc to 2 dashes. So that's VXW is congruent to, and I'll do the same order. So Z to X to Y. Okay, so now the question is, can we say that WV is the same as YZ? So WV would be third and first. So third and first is the same as YZ, third and first. And up here, that's exactly what they wanted. So we know that WV is, of course, congruent to YZ. That's the very definition of congruent triangles, or shortcut, Cpctc. Yes! Woo! Well done. Okay, now let's just do a bunch of proofs. That's it. Lesson over, but we're just going to do a bunch of proofs now, okay? So Z is the midpoint of CT, and we have parallel lines. Okay, so I'm just going to sketch it out first. Well, we know we have vertical angles, okay? Z is the midpoint of CT, tells us that this is congruent to this. And then we have alternate interior angles. So if these are parallel and we have transversals, actually we know both. This angle is the same as this angle, okay? And separately, we know this angle is the same as this angle. We just need to know which ones are they asking for here. So we want to show YZ and EZ are the same. So Y to Z and E to Z. So we want to show that these are the same. So our triangles need to have this as a side. So I'm going to go ahead and say because these are parallel, then this angle is the same by alternate interior. And what that does is that tells us that this triangle matches this triangle, and then we could use Cpctc to say their parts match, right? Okay, so that's going to be my big picture plan. If that was hard to follow, hopefully it's easier to follow when I actually start doing the proof. All right, so let's start with the given. So Z is midpoint of CT. Okay, that was given. And then we could use the definition of that word to say, well then, that means from C to T, it stops along the way. Wow, that was way too big. So C stops at Z. And that was the same as the other half of the journey where we kept going from Z to that other endpoint T. Okay, didn't even need a picture for that, right? Z is just in between the C and the T. And that's the definition of a midpoint. Okay, so that's one of the congruent parts of the triangles. What's another one? Well, another one is, and I'm going to put that down on the same layer here, is I could say angle EZT is congruent to angle, so EZT, so CZY. Okay, and that was the vertical angle theorem. Okay, and now what's that third part? That third part uses the parallel line. So let's start up here, and let's say we know CY is parallel to TE. Okay, and that was given. And then because of that, we could say TEZ, so angle TEZ is congruent to angle CYZ. Oof, that's sloppy. Okay, that was the alternate interior angle theorem, or biconditional, whichever one you would call it. And so now with those three combined, we now know that this triangle is congruent, and that's because we have two angles and a non-included side, two angles and a non-included side, and they're in the same order. So this non-included side is on the side of the one arc. So non-included on the side of the one arc. So that's right, okay, so I'm going to just erase some of these markings here that I did. So just some of these, there we go. All right, so now the order, I'm going to go 2 arc, 1 arc, 1 dash. So 2 arc, 1 arc, 1 dash. That's going to be my order that I do. So that's E to Z to T. And that's congruent to triangle E to Z to T is Y to Z to C. And that was by two angles in the non-included side, triangle congruent, so AAS works, okay? So now what? Okay, I'm just move that over a little bit. We want to see that YZ is the same as EZ. Well, let's check. So YZ, first two letters, same as EZ. Oh yeah, it's because the matching parts match, okay? So YZ for sure matches with EZ, and that's because the two triangles are the same. So all their matching parts are the same. So that's Cpctc. Okay, so I'm just going to keep doing some proofs. So a couple minutes per proof here. So DL bisects BN, okay? So if DL bisects BN. Now, keep in mind, if DL bisects BN, that means BN gets split. It is cutting BN in half. That's the way the verb works. It is not saying that DL gets cut in half, okay? So just because I bisect BN, so here's BN, and if DL bisects it, that means DL goes through the midpoint. But DL could look like this, right? Where way more of DL is on one side. It doesn't have to be perpendicular. All it means is it passes through the midpoint anywhere, right? Okay, so I just wanted to be clear on that. So we only know BN gets cut. We don't know that both get cut. You can say the words bisect each other to mean both bisect, but this is only saying DL is the knife that is cutting BN in half. So what this means is BN to x is congruent to x to n. Okay, so we're probably going to use that to find some congruent triangles. So let's see. So we marked that, okay, and we also have angle XLN. Oh, it's written in the picture already. So XLN is congruent to angle XDB. So I haven't even figured out what triangles are congruent yet. I'm just kind of writing the given and then just defining that word. Okay, so now let's look at the picture. So we want to show LN is the same as DB, just kind of working backwards. So what triangle uses the two pieces of information and has ln and db as sides? Well, this would be the triangle that we want to get congruent. Because if this is congruent, then we know that this must match this, if that's congruent to this one. Okay, so that's our goal. Well, what other piece of information could we use here? Oh, again, we got vertical angles here. So vertical angles, let's go ahead and write that. So we know, I'm going to just make some room here. So I'll shrink this and move over. Oh, and I never even wrote a reason for that. What the heck? Getting sloppy here, Mr. D. Okay, over here we know that angle BXD is congruent to angle LXN. And again, that's vertical angle theorem. You're starting to see which ones we use a lot here. So this was vertical angle theorem. This was given. This was definition of bisects. Or really, if you wanted to say this, it would be really the definition of a segment bisector would be even more clear. Okay, and then up here, this was given. Okay, so now we got the three pieces of information we need. Hopefully, those are enough to say our triangles are congruent. Let's just double check. I'll erase some of my scribbles here. So look at this. We got two angles and a non-included side, and the non-included side is with the 2 arc. So we got two angles, and on the 2 arc side, that non-included. So just going in that order, 1 to 2 to dash, 1 to 2 to dash. That's LXN is congruent to triangle DXB. And that's by AA. Man, we are using a lot of AAS. Okay, let's go do another one here. Whoa, look at this craziness. So this is going to throw back to some segment addition postulate here. Don't be afraid of getting your hands a little dirty with the algebra. Okay, so we know MN and PQ match. And we know M is the same as Q. And we know 2 is the same as 3. Notice that they didn't want to do all the letters, so they just gave it a name with angle 2 and angle 3. So what we want to show is that triangle MLP, we want to show that this triangle is the same as this triangle. Okay, so to get those two triangles are the same, we need at least one side is the same. We don't have a side, so we need to either get that these are the same. We don't have a way to do that. Do we? Do we? Oh, actually, okay, so there's lots of ways to do this problem. I'm seeing we could do these supplements, and then we could get that angle 4 and 1 are the same, and then these triangles are the same, and then that would be enough to show that Cpctc, these sides match, so we would have a side of MLP. That's a cool strategy. Okay, I wasn't going to go that way. Or we could get that out of MLP that this side matches this side. Again, if we proved these triangles were the same, Cpctc, we have those sides are the same. Okay, so we could do that, prove those angles or those sides are the same. But I'm going to do segment addition postulate. I want to show that this is the same as this. Okay, so let's go ahead and do that. So we're going to start with, we've got MN is congruent to PQ. Okay, so that was a given. Okay, and then we're going to go ahead and say that means MN is equal to PQ. Okay, that's the very definition of congruent segments. All right, and then we're going to say we also know the segment addition postulate. So we know that MN plus NP equals the total of MP. And similarly, we're going to do the same thing over here. We're going to say NP plus PQ equals a total of NQ. Right? And both of those are the segment addition postulate. Okay, that's the very definition of betweenness. Okay, so now how can we use this? We know MN is the same as PQ. Okay, so what we need to do though is see that there's this extra N, whoops, I circled the wrong thing. There's this extra NP in both of them. So what I'm going to do is I'm going to take this one and I'm going to add NP to both sides. All right, so I'm going to say, this means, I'm going to make it a little wider. So this is MN plus, and I'm going to add NP to both sides, is PQ plus NP, right? And all I did was add NP to both sides, the same thing to both sides. So that's the addition property of equality. Okay, well now look, the MN plus NP, I'm going to go ahead and rearrange these really quick. I'm going to put this big thing in the middle, okay? And then I'm going to take this, I'm going to slide it off to this side. And then I'm going to take this, I'm going to bring it down here. And now look at what this means. Well, I've got this thing on the left, which is the same as NP. And I've got this thing on the right, which is the same as NQ, right? So when I combine this one on the right side and this one on the left side, and I'm doing two substitutions at the same time, which is maybe bad flavor, but because it's so organized, I think it's clear. So then you get MP equals NQ. That's by the substitution. You could just do transitive twice here. You could say, well, this equals MP and this equals, and then you could do transitive and then you do transitive a second time. So substitution property of equality. Then you go, and what I'm going to do here is I'm going to add another page so we've got room to work here. Okay, so we've got extra room now so we can just keep going. So now that means we could say MP is congruent to NQ. That's by the very definition of congruent segments. Okay, and now that we've got that, that was the hard one that we wanted. We have this side. Well, then we already have an angle here and angle here. Match, so that's two angles and the side between them. And I could draw these separate, right? So this is what I really have. If this is MPL, I have this angle, and this side matches. And if I draw NLQ here, I have this angle, this side, or I mean, these two angles and this side. So that's ASA saying those are congruent. So all I need to do is state the givens there. So angle 2 is the same as angle 3. This was angle 2, and this was angle 3. So that's one of them. Given. And then I have, what do they call the other one? Angle M and angle Q. So we said angle M is congruent to angle Q. That was given. Okay, and all three of those combined tell us that triangle, what was it, MLP, so M to L to P is from 1 to nothing to 2, so from one arc to nothing to 2, that would be QLN. Sure enough, that matched. So MLP, QLN, MLP, QLN, and that was by angle with a side in between, triangle congruent. So just double checking, we got two angles and the side between, two angles, side between. All right, I'm going to come back and actually prove this a different way at the end of this video. So I'm going to pause this and jump back to Zoom. I'll come back in 0 seconds. All right, I traveled through time and I'm back. So let's do two last proofs, one different one, and then I'm going to come back and redo this one in a different way, which I think is interesting. Okay, whoa. All right, so let's do this proof really quick. So we've got that this line is parallel, which we're going to use alternate interior angles. So this angle is congruent to this one, and this one's congruent to this one. We've also got vertical angles are congruent, so these are congruent. And then we're given that EF is the same as GH. So EF, this top side, is the same as GH. So I'm not going to use vertical angles here because I just want to use ASA instead of AAS. No reason. So I'm going to not establish the vertical angles. So let's go ahead and start with, and here's what we'll do. Well, let's do this in blue, okay? So let's go EF is parallel to GH, and then we'll put a little box around that. I forgot a line there. And then watch this. I'm going to split this off and go whop, 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 whop. That means that angle F is congruent to angle G. That's the alternate interior angle theorem, and also E is the same as H. So E is congruent, whoop, that's an angle symbol, is congruent to angle H. And both of those are the alternate interior angle theorem, alternate interior angle theorem, okay, or biconditional, you could call it that if you wanted. All right, and then we also have the fact that we were given that EF is the same as GH. So I'm going to throw that in the middle. Whoa, look at this design. It's like an art form. Okay, so we're also given EF and GH are congruent. So EF is congruent to GH. And then with these combined, we have ASA is the same as ASA above. So this was given. And then we bring all three of these facts together. Gosh, that design is just, I like it. Okay, so ASA, I'm going to go one angle arc to 2 to that middle one. So that's GHK. G to H to K must be congruent to. And then I'm going to do the same thing. So 1 to 2 to nothing. EFK. So EFK. And that's by the ASA triangle congruence. Okay, so now what we need to do though is use that, right? The whole point we got triangles was congruent to get their matching parts. And so we want to show that EK is matching KH. And again, the way we do that is go EK is matching KG. Wait, EK and KH. What the heck? EK. Did I do the order wrong? Let's see. GHK, that's what I wrote, is matching with 1, 2. So FEK, is that what I wrote? I said FE, and then I wrote it wrong. FEK. See, good thing. Order matters, right? So 1 to 2 to nothing. So 1 to 2 to nothing. FEK. There we go. So now EK should match KH. So EK matches KH, yes. So we know EK is congruent to KH, and that's by Cpctc. Okay, so I'm going to go back to this proof, and let's do it a different way this time. The way we're going to do it is use Cpctc in the middle of the proof. So I want to instead show this triangle is congruent to this one as a way to get one of the sides of this big triangle is congruent to the sides of this big triangle, right? So if we want to show these two pink triangles are the same, what we need to do is get one of the matching sides. Last time we used segment addition to get this bottom side, but instead, let's use Cpctc to say the side of this blue triangle matches the side of the blue triangle, but now those are the sides of the pink. So, okay, I know that's a crazy diagram, but our goal is going to be to get these two triangles congruent. Well, we already have two of the facts, right? We have this segment and this angle. So what we're going to do is use these are supplementary here. So let's do that, okay? Well, we know angle 1 and angle 2 are supplementary. How do we know they're supplementary? Well, there's lots of ways to say this, but basically the idea is linear pairs are supplementary, right? Now, in our book, that's called the Supplement Theorem, but every book says that differently. So that can be called the Supplement Theorem, but I'm going to do the exact same thing, except I'm going to do it with angle 3 and angle 4. So angle 3 and angle 4 are supplementary. Again, that's because linear pairs are supplementary. And though, we're given that angle 2 and angle 3 are the same. So what I'm going to do is I'm going to pull this over here. Whoa, I missed a letter? How does that happen? Okay, so I'm going to pull this over here. And now I'm going to say, well, we know that angle 2 is congruent to angle 3, and that was because it was given. Well, look at this. Now we know that angle 1 is supplementary to 2, and angle 4 is supplementary to 3, and angle 2 and 3 are the same. And remember, then we had a theorem that said, well then, angle 1 and angle 4 must be congruent. And that's because, and I'll just write it out because I don't remember if we even named it. So if two angles supplementary to same or congruent angle, then congruent. That was the idea. So if you have two angles, and it's just algebra, right? If these two add up to 180 and those two add up to 180 and 2 and 3 are the same, you take it away, substitution, and then those are the same as each other. All right, so we got 1 is the same as 4. Well, that's enough. Now we can just state the other two things that were given. So M is the same as Q. Well, that was given. And then we also have that over here, and MN and PQ. So so MN is congruent to PQ. That's my like hand hitting these little buttons in the bottom right as I'm trying to work here. So given, okay, and I'm just gonna erase some of this I'm gonna move this out, just rearrange this a little bit, okay, and there we go. So now it's just a little more centralized. Okay, so now with these three together, and I'm gonna move these down because I'm actually gonna reuse it, I think. So I'm gonna put these down a little bit. This is where design and flowcharts are kind of cool. So we can put these three together to say, well then, we know that triangle MNL, so those two side triangles, so triangle MNL is congruent to triangle, and let's get the order right, so M to N to L is the same as QPL, okay, same as QPL, and that was by, well, we had angle, side, angle, and I can't use two, it's got to be three arcs, is angle, side, angle, okay, so that's angle, side, angle, triangle congruence. Okay, and now how are we going to use that? The whole reason we did that, the whole reason we got those two to match, was so that we could get a side. So let's say this side, so it's on the outside, just so it's easier. We could say these two sides are congruent, and then that lets us use angle, or no, I'm saying it wrong. We would use side, angle, angle to get this triangle is the same as, and I'll do it in pink a little off. So then a side, angle, same angle. So those two triangles would match by angle, angle, side, or side, angle, angle. So that's the goal we wanted. So I'm going to state that ML and QL are the same. Okay, so that means ML, first third, is the same as QL. Okay, and that was by Cpctc in the middle of the proof. And then now that we have that, let's state the other thing. So we're going to use those M is the same as Q. So I'm going to reuse this over here, and then I'm going to reuse that, what else am I going to reuse? Whoa, I went too far. I'm going to reuse that 2 and 3 are the same. Oh, shoot, that's going to be hard to rearrange. Well, let's try it, okay? I'm going to rearrange this a little bit. Let's see how this works, okay? Shoo-wee. So I'm going to move this, and I'm going to move this, and I'm going to say, okay, well, now this arrow went from here to here. Okay, so those three combined to there, and then I'm going to swap these two over here, okay? So I'm going to take this one, and I'm going to put it over here, and I'm going to, yeah, there we go, okay. This is crazy town, but I like that I can just rearrange it. It's so much easier than working with pencil paper. Okay, so those three combine to get that one, and then I'm even going to slide this down even lower and put it down here. And then we've got, we can just erase it and put the arrow. Okay, so it still has those three combined, but now we can use these three facts together to say with these three, 2 matches 3, yep, that's the angle with 2 arcs, and then M and Q, that's angle with 1 arc, and then those sides, with those three together, we use angle, angle, side, triangle congruence to state, and then what is it? The MLP, let's just double check, so 2 arc, so we start with the 1 angle, we go across the 2 dash, and then we go to the 2 angle last, so that's MLP, and then QLN. So we start with the 1 angle, across the 2 dash, and we end at the 2 angle. So that is right, MLP, QLN. So MLP is congruent to QLN. Oh man, what a cool proof. I just wanted to do it in 2 different ways just to show you. And we did a lot of like rearranging there. You also could have just restated the given a second time. I think that's just a little inelegant. I think instead doing it by rearranging is a little more fun. It's like a little mental puzzle. How do you get these all to click? And it doesn't have to go top to bottom because they have arrowheads pointing. So you could rearrange this sideways, vertically. It's just so cool. What if though, instead of 2 dimensions, what if we did a flow chart in 3 dimensions? How cool would that be? So now you could pull like one of these things forward and the other backwards, and that would give you another dimension to kind of create arrows. All right, so I hope you enjoyed that video. Good luck, you guys.